All right, good morning, and I hope everybody enjoyed your semi day off yesterday as we just continue on the fundamental theorem for line integrals. So, we're still talking about line integrals, but today we're talking about okay, what if we have a line integral where our vector field is um, the gradient vector field, or what if we're doing a line integral over a conservative vector field? Well, this brings us to the fundamental theorem of calculus, or we call it the part of the fundamental theorem of calculus, all right, where we can take the integral of some derivative of f dx, and when we have, some derivative inside the integral, which when we integrate, we're just going to get back to the original function, and then we take the two endpoints, and we take the net change of the two endpoints. Well, that was the fundamental theorem of calculus part 2. Well, now we're going to have the fundamental theorem for line integrals. So, why are gradient vector fields so awesome? Because gradient vector fields are the conservative vector field. And if we think of the gradient vector del f of a function of 2 or 3 variables as a sort of derivative of f, again, because to get to gradient vector, what you would be doing is you're taking the partial derivatives of your function. So a gradient vector is like the partial of x, I, plus the partial of your function with respect to y, j, and then if you have a z, the partial of your function with respect to z, k. And that's your gradient vector. Again, the gradient I don't know, the gradient is a vector, and then when we take, the partial derivatives, we're getting a vector field. And so then the following theorem can be regarded as a version of the fundamental theorem for line integrals. So if you recall, again, I'm going to try to write this. I'll just write this right here. All right, if we have a line integral, writing this with my finger, f is considered the vector field. All right, dot dr, where dr was giving us our, our arc length. And so if we're trying to find the line integral on a conservative vector field, it's just, the integral from a to b. That's a b. How did that little dot get there? I don't know. So from a to b. Then what we can say is, well, if f is now the conservative vector field, then we'll just say del f, and we'll replace our cap f with the vector field with the gradient f, which is the conservative vector field. And because we're considering that, a derivative, then when we take the integral, when we take the integration, we'll get back to the original function, which is f, and we just plug in rb minus r of a, plug in our two endpoints, and that's our line integral, right? So just using the fundamental theorem of calculus again. Now here, let's get off of this pen now. All right, here's like why. Well, here you can see just a short little proof of it, where we have, the line integral of our vector field, but here our vector field is the gradient vector. And so when we integrate this, if we're considering that the gradient vector, then we can see our dot product down here as f, which again, f is going to be defined in terms of r. And then dr, we can if we take the derivative of, r, it's going to be r prime of t dt, because r is going to be in terms of t. Then that's just equal to the integral a to b, and then the partial of f with respect to x times the partial of x with respect to t as we do the dot product. And then what we can do is we can pull out a d over dt, and then we have a d over dt with the dt of the integral. Well, that's going to cancel each other out, and we're going to be able to take the endpoints f of rb minus f of ra. All right, so example 1, the gradient of f. If we have a gradient and we're told that that's 3y minus 2x and 3x for ct, and t and x is t and y is 5t for 0 is less than or equal to t is less than or equal to 2. Verify that f of x, 3x y minus x squared is a potential function. All right, so here we have the gradient vector. Let me get a pen out so I can underline a few things. All right, so the gradient f is just the partial of f with respect to x and the partial of f with respect to y. And so here we have the partial derivative of f with respect to x and the partial derivative of f with respect to y. Now, if I want to find the original function, if I want to make sure that this is going to be the well, I guess I'm told that this is the gradient function. I want to find, the potential function. And we expect this to be what the original f was. So because we're given this, if you want, you could just take the partial derivative of that value with respect to x and with respect to y. If we do that, you're going to see how we get 3y minus 2x and 3x. And so again, we can find it going one direction. We can take the partial derivatives of f, and we'll see if that gives us, our del f, and it does. But I'll go ahead and erase all that. Another way to get there, and this is what we're going to do kind of on the last page, but another way to get there is, okay, if they give us the gradient vector, then we're assuming, or they give us any vector, we're assuming, okay, that if they tell us that we're on a conservative vector field or we have the gradient, that this is the partial derivative of f with respect to x, and this is the partial derivative of f with respect to y. So what we can do is we can say, okay, let's take one of those. We could take 3y minus 2x, or we could take 3x. And we're going to go ahead and set that to one of the partial derivatives. So we're going to say, okay, well, the partial derivative of xy is 3x, because that's the gradient f. We could have said, the partial derivative, we could have said f sub x is equal to, and then we could have set that equal to 3y minus 2x, but I chose the one that was going to be the easier one. Again, they're both pretty easy, but so what we do is, okay, we take the antiderivative. So we're going to take the antiderivative of f sub y, and when we take the antiderivative, we should get f of x, all right? And we do that, but again, since it's partial with y, when we take the antiderivative of this, we're doing it also with y. So 3x becomes 3xy. But then we have to add in plus g of x, because we don't know what g of x is. We know that there could be a function of g of x because we took the partial with respect to y, so we have to add in that g of x. So when we take the antiderivative, we have to include plus gx because we took it with respect to y. All right, same thing. If we did this with f sub x, all right, and we took the antiderivative, then we'd have a plus gy instead of a plus gx. All right, so we have f. So then from here, we're going to take the derivative of this, but now we're going to take it with respect to x. So we go ahead and take the partial derivative of our function with respect to x. We do that, we're going to get 3y plus g prime of x, so that we can actually solve, okay, well, what was our g of x? Now, we know what our partial should equal. Our partial of x should equal our 3y minus 2x, because we're told that that's the partial from the gradient vector. And so we set those two equal to each other so that we can solve for g prime of x. So we set these two equal to each other. The 3y's will cancel out, and we're left with g prime of x is equal to negative 2x. And therefore, you can say, oh, well then now let's take the antiderivative of this. The antiderivative of g prime of x is g of x. The antiderivative of negative 2x is going to be negative x squared. So we found g of x. So g of x is negative x squared. We can plug that back into our function f of x, so we get 3xy plus g of x, which we said was negative x squared, and so we have our final potential function. All right, so there's, the other way. A lot of times you're not going to be given, you're going to say that, hey, we're on a conservative vector field. We need to find the potential function. And the reason why we need to find the potential function is so that we can actually do the second fundamental theorem of calculus. All right, so now we're going to integrate. So to integrate this, we have r of 0 and we have r of 2. All we need to do to find these values is to plug these in to our c of t. This really should say r. Instead of saying c of t, it should say r of t. All right. So when we plug those values in, we're going to get, for when we plug in 0 for t, we're going to get 0, 0. 0t is 0, 5 times 0 is 0, so that's how we get 0, 0. Then we're going to plug in 2. And so plug in 2 to t, it's just t. Plug in 2 to 5t, it's just going to be 10. So here we get our two values for our endpoints, for our r. So 0, 0, 2, 10. And the reason why that's important is because when we go ahead and find the line integral but using the gradient vector, again, that's just going to be f of r of 2 minus f of... Let me show this because I didn't write this. So when we take it, it's just going to be f of r of 0, sorry, it should be 2 first. 2 minus f of r of 0. And that's what that is. So f of r of 2 is going to be f of 210 minus f of 0, 0. That's 0. And when we substitute these in, we put these into our potential function. The reason why it's called a potential function is because you don't know if you have k's or not. It could be plus k, it could be minus k. And so that's why it's called the potential function, because when you take a partial derivative, you could get rid of, k. And we'll kind of go ahead and go over that in the last page. So we plug them into our function. We plug in 2 for x, 10 for y. We're going to get 60 when we plug that in. When we plug that into x, x, and then the second part's x squared, so 2 squared is 4. So we get the 4, and then minus, and then this is going to be our partial. Alright, I'm sorry. I had to pause real quick because I'm wondering where this 3 cosine 0 minus 0 squared is coming from. And it's coming from nowhere. So it should be minus, and then we plug in 0, 0. It's going to get 0, 0. So we're still going to get 56, but I don't know where that came from. And so again, we should just be plugging in to our potential function that's right up here, and that's definitely not 3 cosine of 0 minus 0 squared. Oh wait, that's not cosine, that's a 0. All right. I was wondering, why does that say cosine? It's not cosine. It's going to be 3 times 0, 0 minus 0 squared. All right, and so we get 56. I'm sorry, it's pretty early in the morning, and I was wondering why that says cosine, but it's not. It looks like it says cosine, but it's not. All right, so that's page 1.